routine. There are. I'm making a mistake maybe. So I should say, when I say this acts entry-wise and preserves positivity, I mean for all n. For all n. That's important because the fixed dimension problem is, I mean, it's not just a rookie mistake, it's actually a serious mistake because n equals to 3 is still open. So uh, n is equal to 1 is very easy, just entries to entries. That is open. N is equal to 2. Fixed dimension, n is equal to 1, easy. N is equal to 2. With some effort, but doable. Vasudeva. If I need this result, I'll state it, but right now I'll just say it is done. But n equals to 3. Okay. Why I'm saying this? Because when we go to totally non-negative and totally positive matrices and preservers of those, we'll see that not only they have settled it for all n's or all d's, I'll tell the notation there, but also for all fixed dimensions. Let me state the problem here.
The other blackboard.
Here, inside.
There's a blackboard in the middle.
Yeah, but this will remain. So let's ask the same question for Tn. Okay, now we have to define Tn matrices, but I think we know by now. But, okay, let xy be. I'm writing on this board so that I'll not erase it and it will be here if you want to go back and see. The totally ordered sets. Then a function or a kernel k from x cross y to r is of the n. If we take it for any n, x1 through xn, x and y1 through yn in y. If you take this and consider the matrix k xi yj, this n cross n matrix has to be a determinant of this matrix has positive determinant if it is TP, and it's non-negative determinant. The problem is same. So problem is, suppose we want to classify this f from, let's take R to R. I want to see when does this maps the Tn matrices into itself or TP, or when does it leave it leave Tn or TP invariant. Let me just. This is on x cross y, but I'm taking right now. It's, if I act entry wise on the matrices, and that's, we have this. That's the same question. Classify the functions. Let me state the result now. Oh, I shouldn't have. Okay. This, you'll see this more than one time. This is just the first of many times. Again, the same setting for matrices. F 0 infinity to R M and numbers, and let's say D is then the following are equivalent. And the following are equivalent. First one is, of course, this F maps or F preserves positivity on M cross N Tn matrices. If and only if this one, we can only take, since D is the minimum of M and N, we can only take D cross D minus of these matrices, right? Even if I have M cross N matrix, a rectangular matrix, I can only take these many minus of that size and lower, of course. So preserving positivity on these matrices is same as on the D cross D matrices. This is the non-trivial part. F is either a constant, non-negative constant, or depending on what the values of D are. Write down here. This is not really hard. Equal to 2. And C and alpha are non-negative, or fx is identical. But then our functions are on close zero, open infinity. So this makes sense. Like this is not a constant function, just it's indicator of x positive, the positive real axis. So it will put 0 at 0, 1 otherwise. C positive alpha greater or equal to 1. And this is the best case for me to write. So D being 4 and above, we just get this function. So just the linear maps. Negative, positive constant, because non-negative I have included here. This is the complete here. We'll do one by one. So note that now again go back to the fixed dimension here. Look at the n equals to 2 case here. Actually it is, so it is something called as the functions are non-negative, multiplicatively mid-convex. That just means you take you take that function, define new function log of f of e power x. That has to be midpoint convex. And continuous it becomes already. And non-decreasing, that is the characterization for fixed dimension here. Here it becomes so easy. And after that, I mean what? Proof. One. So as we saw, one if and only if 2 is obvious. So that if we assume 2, then for 3, if it's no, let's assume it's non-constant. D equals to 1, this is obvious. Let's try this. I mean, in his talk, Professor Khare did that case actually. Yep. But D is equal to 2. I should say things, then all. It's an important case, but it will take too much time, too much of my time. So d equals to 3. So I have to rule out this possibility that it's a heaviside indicator and alpha between 0, 1. This I have to exclude these two possibilities. Right. So consider this matrix. I hope no one doubts it's Tn, but one. Yeah, determinant is 0. If you apply a heaviside indicator on this, Tn, this. If you apply, forget about the constant for a while. If you just apply this, then this becomes 1, 1, 0, 1, 1, 1, 0.
What we apply?
Indicator. Indicator of x positive. So 1 remains.
Yes, okay.
Yes. 1 by root 2, just this becomes 1. That's all. And this has determined minus 1. Only from here it will contribute. So it is not a T and 3 cross 3. So this case gets ruled out. Similarly, very coincidentally, the same matrix gives that even alpha between 0 and 1 is not possible. Let's apply and see. If you apply x power alpha, determinant of f of a is, I know it actually. So alpha between 0 to 1, this is negative. Right? Negative cases. So alpha has to be greater or equal 1. That is, so this suffices is a result by Pollard, Johnson, and Flockhart. I just state it here. Converse is due to that the functions c x power alpha, where c is positive and alpha is greater or equal 1, preserves En on 3 cross 3 is a result. So I'll use that. Right. For the greater or equal 4, even the equals to 4. Same paper, they make some clever choices of matrices. They consider a matrix. It's a very big matrix, so I'll avoid to write it, but then it's also done in this. So I proved, really I didn't prove anything. I just ruled out some cases because this was done. This is I ruled out, and the converse is in this paper, and same in the same paper you have this also. So oh sorry, what am I doing? This I should have. Why am I just applying x power alphas? I didn't tell you. D equals to 3, okay. But why the preservers? I mean, I just said I have to remove those two functions and I'm done. Why is that? It's because any 2 cross 2 Tn can be seen as a 3 cross 3 Tn. How's that? Just padding by zeros. And this will be very useful. Should have said this. Let 2 cross 2, 0, 0, 0. This is a 3 cross 3 matrix. Is right. This we have seen, I think, multiple times. So if it preserves on d equals 3, it has to preserve on d equals to 2. So we get these two functions from there and we rule out by this. Now I have done something, I think. Okay, so Tn. So for let's say what is Tn of order some fixed p, let's say. So Tn of order, I'll say xy again total order sets. This is TP p or TNP. If I take just the n less equal p, I do this. So all 1 cross 1 minus or 2 cross 2 minus till the point all p cross p minus are has determinant are non-negative or positive. Depending on that, I'll say it's the TPP or TNP. So this result theorem 1 suddenly becomes 2 also, because we can what we can do is we can put p here everywhere. Just by padding by zeros. I can pad by zeros and get the same result.
P equal to 1.
Right. Yeah, yeah. So then,
Go for it.
thank you. Similarly, for kernels, x cross y, it is TPP. I've been taking just the matrices, right? M cross n matrices. If I take the kernels on x cross y, any totally ordered set, I can do the same thing. Padding by zeros, I can just remove this and go for the same. I won't write it. It's okay. This here comes the non-trivial part. Let's ask another question. What about the inverse of EP? I mean, depending on here. Here we cannot just, even if we, so we have the 2 cross 2 result because the other day he did it again. But here we cannot just pad by zeros. Zero entries are not allowed in TP. So just TP 2 cross 2 cannot be just this important observation here or important tool here. We have lost it. Or we lost it. So let me first state the but same result hold in a similar spirit. Let me make you good use of board. Let me make this TP. Now the constant cannot do it. If I apply a constant function on a TP matrix, then it will give me a constant kernel or constant matrix. It's not TP. Determinant is here. So this is first one. It has to be positive. Then this is not. Again, because again, it's a heaviside indicator. There is no zero in the domain. F is from 0 to n, open 0 to. So that function is gone. That's it. The proofs are a bit more and different. Let's try to prove that one. First state for not orders. Let's just do this. Then it is one if and only if two is it clear? Two. For b is equal to just fx positive is clear. B is equal to 2. This was done. F of x is But even from here, it's hard to get for the other ones. So we recall how did we I mean in that talk the day before yesterday, how did he prove this? He considered two preliminary results to this. First one was, let me just remove this. Any 2x2. Then it can be embedded into a generalized Vandermonde. Generalized Vandermonde kernel. I will use this. This is a TP kernel. This is of the form e power xy or up to scaling. So this result he used, and a very important result of density approximations. What we'll do is we'll go from TP, the result for TP to TN. But for that we need some sort of density which was given by Whitney's density. Which is TP. It's even true with the orders. Let me state it that way. That's so given any M cross N matrix, which is NP, we can get a sequence of TPP, which converges the pointwise. Oh. So using that, he wrote this result. Now let's say, or even this he did. Now for d equals to 3, what can we do? Same thing, because any 2x2 Tn, if it preserves TP 3x3, we can take the generalized Vandermonde of 3x3, then TP 2x2 inside that, right? So it has to preserve TP 2x2. Then by that result is, or I think he said it here has to be. So f has f extends continuously 0 infinity 0 infinity. But so it preserves by Whitney density. It preserves Whitney density and the continuity. It preserves Tn 3x3. So the Tn result we have. And similarly for d equals to 4. Oh,
That's the test alarm.
Okay, it's just a test.
This is a test.
Test the file.
There we go.
Really?
Maybe. So it's the scheduled test.
I don't know.
Please.
She also did test as only a test.
I prepared to say that I knew this was going to happen. I was going to say this talk is a fire. But then I
Oh, we're all really alert.
what can be the, so if we have a Tn kernel, suppose on x cross y, what can we say about sizes of x cross y? It could be anything, right? I mean, we can take the zero kernel, for example. You give me any totally ordered sets, I can take the zero kernel. So it is a Tn kernel on that x cross y. So we cannot really say anything about the sizes of x cross y. But here, for TP, we have a proposition. And suppose xy on empty, fully ordered. In the following are equivalent. And number one, yes, there exists a TP kernel K from there exists a TP kernel. P greater or equal to. It's almost a, I mean, 1 implies 2 implies 3 is, I'm just killing the time I feel, but I need it.
That's why.
Oh, sorry. It is true for x plus x also. This is important. Either x or y, the singleton. Or big or. There exists an order preserving injection from xy to 0. So I'm saying if we know that there is a TP kernel on x cross y, we can say something about its sizes. I'll prove this. It's easy and but very amazing. So till then, 1 implies 2 implies 3 is hard work is not there. I think it's pretty easy, right? If it is a TP kernel, it is of course TPP and TP2. I mean TPP for P equal to. So it is. Let's do 4 implies 1. If x or y is singleton, just take the take k is identically equal to 1. So that will be a kernel on that, right? If not, suppose this is not the case, then there exists a order preserving bijection. This. So now we take the kernel Vandermonde kernel on 0 infinity cross 0 infinity. Consider. So basically x and y are identified with subsets of 0 infinity, right? And on 0 infinity cross 0 infinity, we have the Vandermonde kernel. So by just composing the map, we have a kernel on x cross y. So composition and using Vandermonde GVM, generalized Vandermonde kernel. Yeah. Non-trivial part is this. 3 implies 4. Okay, I proved 4 implies 1, 1 implies 2, and 2 implies 3. It's obvious. 3 implies 4. Let's assume x and y are not singleton. And then let k from x cross y to R be TP2 kernel. Fix y1 less than y2 in y. And consider the following. define this by phi of x, it's just the ratio function. Right. Now, if I take x1 less than x2 here, what is phi of x1? I'm claiming this is less than this. But that is true because if we cross multiply and say this is exactly the determinant of this. If we consider this matrix. Once. So TP2 kernel, I have chosen x1 less than x2, y1 less than y2. This is the TP2 matrix. So this is a TP matrix. The determinant of this is strictly positive, which is this. So it's a strictly increasing function. So it's an injection. So we can either fix a interchange x or y and see that this happens for y as well. So we get the math. Am I clear? Is this? So phi is increasing. So we have this. Yeah. We can change rules of x and y if needed. Yeah. Okay, I'll speak about the kernel case here, but I think I should go to this multivariable case and I'll come back. So suppose say A is in B and Pn. And I have map E1. Define f of A, B, C to be again the entry wise. Then question is which functions like Tn 11 plus Tn, let's say 7 and 24, 2, say some other thing. It's just today's date, by the way. I didn't and then other numbers. Yeah. So we answered this question in the several variable case. Uh, Not just for matrices or kernels as well. And let's take the general question. Or generally we consider one same question. Which functions take t and k1 through t and kp to t and k. Yeah, for simplicity. They just take two variables, p equals 2 and k1 equals to k2 equals to L. I think that's if someone remembers what was the answer for one variable and en case, it was just the cx power alpha and the indicators, the heaviside indicators. In this case, is the for two cross two is the same answer is the same, which is for so if we just have the answer is alpha beta positive or C or all the multiplication, all the possible combinations of all those heaviside indicator and power function. This is just by induction. If you restrict, so for Tn, and if you take a two variable Tn preserver, you restrict it to one variable. That is, if you take one variable to be constant, the other variable is a preserver in the lower dimension. So by that we come back to this case. But the dependence on the constants are there. The constants are constants are dependent on the variables. So we have to rule out some cases. That is done by case on the paper. Let's non-constant alpha, beta, positive, C, positive. Okay. The next case. Suppose we have this. And we have padding by zeros available to us. So these four combinations are there. But then we can again use the matrix that we used in the Tn case. That's like A1 to B or A to B one by, I hope this. These all ones. This is a matrix with all ones. If we apply, if we apply these functions, this by swapping, if necessary, this we see that these indicators are not possible. So the only possible case is this, and we show that only one power is possible from this also. Say the only possibility is for alpha before beta. My claim is we don't have these such things. We just have single powers, which is by we take these matrices. Remember, if I apply this, if I take this matrix 1, 1, 1, 0, 1, 1, 1, 0, 1. This is not determinant of this is negative, so this is not cancelled. So what we do is we just take this. Okay, somewhere I have to put 0. Sure. 0, 1, 1, 1. Right. If I take test matrices to be this now, A and B, apply it here using this function. I take F to be this. Take test this to be A, this to be B, we get one, 1, 0 power. In some order, alpha and beta will get, but those are positive numbers, so it is just so even these powers are not possible. Okay. Yeah. The real issue arises when we need something like Whitney density for TP kernel, or it is not known that for matrices it is known, of course, but TP x cross y, whether it is dense on TP x cross y is not known, for x and y being arbitrary sets. So we'll need some substitute of that in. So let me first tell that theorem. This is substitute for this, or quickly like. So n r and any bounded is important. Any bounded kernel can be the convergence is locally uniform at the points of continuity. So continuity. The sequence of minor PPP. So this serves as a substitute result to the Whitney density for all. So we use this result and move forward for other cases for the kernel case. So first thing, how to use this result? I mean, it looks a bit tricky to use this because we have so many conditions. We have local uniform convergence, even that is on point of continuities. So if I just start with a matrix, let's say I start with, so what I want to do is I want to do the same characterization for TP kernels. Now I cannot just pad by zeros again. I start with a TN matrix padded by zeros. The matrices that gave us counter examples, or those gave us single power functions. Those, but even there we don't know if we can directly approximate this. So what we do is we make those points to be points of continuity and then approximate. So how to use this? So let XY be totally ordered sets, and suppose we have a TP kernel on it. So since we have a TP kernel, without loss, it is a subset of 0 infinity. Otherwise, I can take an injective map and say that. So suppose some D is TN. Right. I want to see how to use this result in matrix. So consider this. X1, X2, XD, Y1, Y2, YD. And we have these points. AIJs are sitting here. Let me do this. This is better. What I do is I define the new kernel used in these boxes. And I make the, using this, these are AIJs by the way. At these points, we have the entries AIJs. So I make it constant on it. These are A1, 1, A2. Yes. So now these are actually points of continuity. This new kernel, right? So let me write it formally. Let XD in X let epsilon positive be such that epsilon is of course positive and less than mean of So these are the epsilon, so that it will be separated. These are distinct points. These are discrete. What I do is I take this A. Add it by zeros. Now this is a Tn on X cross Y. Tn.
Just a matrix.
Yeah. Oh, you mean I should write the kernel. Oh, sorry. So I defined this kernel K A using this. So I have the original and zero otherwise. It's fine. It's now we have kernel where these points are of points of continuity. So we can have by this result, a theorem. Correct this there. Then take 1 minute of TP kernels. That AA converge to at xi in particular. And I produce the result for TP also using this. I think I'll stop.
Okay, thank you. Thank you very much for your talk. Again, time for questions.